Hello everyone. In the last video we looked at the nuclear stability of different elements and different isotopes across the actinide series. In this component I want to look at what happens when nuclei decay. Our understanding of this area of science goes back to the dedicated and innovative scientists like the Curies, Marie and Pierre, who used chemistry to isolate new radioactive elements, and it was, amongst others, Paul Villard and Ernest Rutherford who studied the radiation emitted by these new materials. In fact, the three basic types of radiation that you learn about at school were really first understood by these two individuals. And before being able to determine what the radiation really was made of, they realized that they could categorize radiation by its ability to penetrate matter. Alpha radiation is stopped by a sheet of paper, beta by a sheet of aluminium, and gamma, the most penetrating, requires a sizable block of lead. This is a testament to the different character of these types of radiation. Later on, it was determined that each type of radiation was a stream of particles, and their masses and charges were determined. Rutherford actually determined that the alpha particle was a helium nucleus. Beta radiation turns out to be a stream of electrons, and the most penetrating gamma radiation is a high-energy photon with no mass and no charge. Although these are the types of radiation that we learn about at school, they are not the whole story. In this video we will look at these three more common types of radiation and the radioactive decays that cause them first, before we look at other decay mechanisms. So, gamma radiation is just a photon, a type of light, pure energy. It is emitted from a nucleus in just the same way that light might be emitted from an atom. Like all atoms, nuclei can exist in a number of different quantum states. Energetically, the lowest state is the ground state, and the excited states are all higher in energy. By comparison with the excited states of atoms, the excited states of nuclei have very large energy separations. A nucleus in an excited state may relax to the ground state, but since energy must be conserved, light is emitted. It's just that it's a very, very large amount of energy, and so a very high frequency light. So with a gamma decay, there is no change in the composition of the nucleus. It has the same number of protons and neutrons after the decay as it did before. Although there is no change in the atom's identity, gamma radiation often accompanies other types of nuclear decay. For example, a nucleus may be transmuted by alpha decay, and it may be that the new product nucleus is in a high energy state, which then relaxes to a nuclear ground state by gamma emission. You should know that there are some useful nuclear spectroscopies that involve the absorption of gamma radiation. These can even be useful from a chemical perspective, not just from the point of view of nuclear physics. So something like Mossbauer spectroscopy tells you about the environment of a nucleus, whether it experiences an electric field gradient, or if there is an unpaired electron causing a magnetic field in the nucleus, that sort of thing. So if gamma radiation is the most penetrating, alpha radiation is the least. What's happening here is that an unstable nucleus spits out an alpha particle. As I said, it was Rutherford who realized that this alpha particle had the same mass as helium and a charge of +2, a helium-2+ ion, and later on that it was simply the nucleus of a helium-4 atom. This unit, 2 neutrons and 2 protons, is a very, very stable configuration of nucleons. Ever wondered why beryllium-8 doesn't really exist? Well, the explanation is down to the stability of the alpha particle. So what's going on? How does the nucleus expel an alpha particle? Well, you should not think of the nucleus as a static thing. The protons and the neutrons are moving, but in a quantum mechanical way. Now the strong force, although it's very strong, is also very short range. And what happens is that there is some small but finite probability that an alpha particle tunnels through the energy barrier and finds itself outside of the nucleus, in a place where there are dominant repulsive electrostatic interactions between the protons in the alpha particle and the protons in what remains of the nucleus. The repulsion accelerates the two particles away from each other, although the shared momentum means that the light alpha particle will travel fast, while the heavier nucleus will have a much smaller recoil. The effect of taking away an alpha particle from a nucleus is that the neutron number drops by 2, and the proton number also drops by 2. This process actually happens in a very controlled way in most homes. We use americium-241, which is an alpha emitter. The process generates a constant stream of alpha particles, a constant current if you like, inside a smoke detector. When smoke gets between the source and the collector, some of the ions get scattered and blocked, reducing the current, which triggers the alarm. Did you know that? Inside your smoke detector in your house is a wholly synthetic man-made element, americium, and traces of its decay product, neptunium. It's probably a good time to start to talk a little bit about the maths part of the rates of decay for radioactive materials. We normally just state the half-life of a particular nuclide, which is an easily understood concept, but I want to link it back to reaction kinetics. First of all these simple radioactive decays, which are not triggered by anything else, are completely analogous to the kinetics of first-order chemical reactions. So you've probably seen all of these equations before. A nucleus has some finite probability that it will undergo a decay. So the rate, as in the amount of nuclei that undergo such a decay over some fixed period of time, depends on how big my sample is. If your sample is twice as big as mine, you will have twice as many decay events. So the rate of change in the quantity of a sample of a particular nuclide is proportional to the amount of those nuclei. To be honest, you could measure the amount in terms of atoms, or moles, or kilos, or pounds and ounces if you wish. The equation that shows us how the quantity changes over time is simply an exponential decay, where the index is the negative product of the rate and the time elapsed. The pre-exponential term, n subscript 0, scales the curve to fit the quantity of stuff that we started with at time 0. So here the Greek letter lambda is our decay rate. Often in chemical kinetics of reactions we use the letter K to represent this quantity. The inverse of this decay rate, by which I mean the mathematical 1 over the decay rate, or 1 over lambda, gives us a quantity with units of time, or perhaps more strictly, time per atom. It is given the Greek letter tau and actually represents the mean lifetime of our decaying species. So we often rewrite the exponential decay in terms of tau, mean lifetime. So what's the connection to half-life? Well, half-life, that's kind of our invention. I mean, we could have chosen third life, time taken for it to decay to 1/3 of its original value. Or if you want to go decimal, perhaps 10th life. Hang on, I feel I'm getting off topic here. Half-life it is. The decay curve can be mathematically created with any base we want to use to write the decay function. If we choose to measure time by half-lives, we choose to replace the number e by the number 2, and tau becomes replaced by t1/2. So the half-life, t1/2, is directly related to the mean lifetime tau. That's all good. Let's try it out. Let's use the smoke detector isotope americium-241. Its half-life is 432.2 years, so it's quite straightforward to work out the average lifetime for each americium-241 atom. We can do it in years, which is meaningful to us, or if you like scientific notation, you can do it in SI units of seconds. From this, we can work out the decay rate, the kind of probability of decay within a period of 1 second. Let's apply that. Just how radioactive is my smoke detector? Well, these days they all contain 0.29 micrograms of americium-241. Okay, of course this value will decrease with time, but to become half of this value your smoke detector has to be 432 years old, so antique. First up, change micrograms into moles, and then moles into the actual number of atoms in americium-241. Since we know the decay rate from above and the number of atoms that we have, we can work out how many decays, on average, we should get for each second. This gives us almost 37,000 decays per second. Actually, decays per second is the radioactivity unit of the becquerel. And what's nice about that is 37 kilobecquerel matches what it says on the warning label on my smoke detector. Okay, what about the third type of decay, beta emission? This is a bit curious. The beta particle is an electron, but it's come from the nucleus, which is odd, as there are no electrons in the nucleus. In fact, it has come from a neutron. Neutrons are not as fundamental or stable as protons. As far as we can tell, protons are indefinitely stable. No one has ever knowingly witnessed a proton decay, and certainly lots of people have been looking. On the other hand, a neutron, on its own, has a half-life of about 10 minutes. It undergoes beta decay to give a proton and an electron. In this reaction, just like in chemistry, mass is conserved. Also, charge is conserved. There is one slight problem. Angular momentum, i.e. spin, should be conserved. But here, as we've written it, it's not. And this tells us that there is something wrong with our equation. In fact, we're missing an electron antineutrino. This has zero charge, next to no mass, but a spin of 1/2. Now spin is conserved. If this looks a little bit odd to you, remember, spin is a vector quantity, so we're either adding or subtracting these spin halves. So although the free neutron is not stable, when a neutron is bound to other nucleons in a nucleus, it may or may not be stable. So the 7 neutrons in carbon-13 have never ever been observed to decay. By contrast, one of the 8 neutrons in carbon-14 will undergo a beta decay in this nuclide. So any nucleus that undergoes beta decay has a change in identity. One of the original neutrons becomes a proton. So the isotope mass number remains unchanged, but the number of protons in the nucleus increases by 1. Okay, so these are the 3 common forms of radioactive decay. When beta decay occurs, it follows the same first-order rate laws. Now before we move on, I need to introduce another process. Sometimes a nuclide will undergo a decay where its mass stays constant, but the atomic number decreases by 1 unit. This seems to be the opposite of beta emission, so we'll call it inverse beta decay. What on earth is going on? Actually, there are 2 separate processes that can occur that give this result, and so we refer to them both collectively as inverse beta decay. The first process is actually electron capture. We know that an electron in an s orbital has a finite probability of being at or in the nucleus. Normally at this point in the orbital the electron has its maximum kinetic energy, but sometimes it may combine with a proton to become a neutron. And if we add an electron neutrino, then mass, charge and spin are all conserved. The other process with the same outcome is positron emission. You know the positron, the antiparticle to the electron, same mass, same spin, opposite charge. Of course, being an antiparticle, if it collides with its normal counterpart, they will annihilate each other in a burst of gamma radiation. Although this seems very novel, and most inverse beta decay occurs by electron capture, positron emission is not that uncommon, and it does have applications. In fact, only yesterday I passed by the PET centre at Garton Naval Hospital in Glasgow. PET? That's positron emission tomography, a medical imaging technique based upon this decay mechanism, but usually using fluorine-18 as the radioisotope. For each different nuclide, if it is not stable, we can identify the principal decay mechanism. We can plot these decay mechanisms on a plot of neutron number n versus atomic number z. First of all, in this image, stable, non-radioactive nuclei are represented by black squares. It's a very narrow line, which is approximately n equal to z for the first 18 elements, beryllium excluded, but it deviates to higher proportions of neutrons as the number of protons increases. This line of black, stable isotopes represents the bottom of a valley of stability. To the north, we have isotopes that have an excess number of neutrons when compared to the stable isotopes. These overwhelmingly decay by beta emission. That's all the nuclei represented by blue squares. This type of decay leaves a daughter product that is 1 square southeast on this plot, which is always closer to the bottom of the valley of stability. To the south of the black stable isotopes are nuclides that have proportionally too few neutrons, or to put it another way, too many protons. When we look at these elements, they overwhelmingly show inverse beta decay, a mixture of positron emission and more often electron capture. That means the daughter product of these orange coloured isotopes is 1 square up to the northwest, again moving us a bit closer to our line of stability. So you see, the decay mechanism that is experienced by a particular nuclide is not random. It is directly related to its position on this plot relative to the position of stable isotopes. Now there are some other rarer decay mechanisms that you should also know about. With nuclei that are extremely neutron rich, there comes a point where there is no more energy gained by adding an extra neutron, i.e. it becomes energetically more stable to separate the neutron. So these elements on the upper edge of the neutron rich side decay by simply losing a neutron. This neutron emission marks the limit of stability of nuclides. We call this boundary the neutron drip line. We know where it is for relatively low values of Z, but its location has not been discovered for elements beyond about silicon. Conversely, on the proton-rich side, there comes a point where adding another proton does not increase the stability of the nucleus over the separate nucleus and a separate proton. Elements at the southernmost edge are at this limit. They lie on the proton drip line, and here these elements decay by emission of a proton. This part of the N versus Z plot is better known, and the proton drip line can be followed along for all stable elements. There are a couple of other colour-coded mechanisms on this plot. Yellow squares represent a nucleus that decays by alpha decay. The alpha decay moves an element 2 squares in a southwesterly direction towards a more stable, lower mass element. And you will notice that all of the yellow squares are found for relatively high atomic masses. There is another way to reduce the mass of a given nucleus to a much more stable configuration. This is much more extreme. The fracture of a whole nucleus, nuclear fission, produces daughter products with much lower masses. This decay mechanism is seen at the very high mass end of the periodic table, and is observed for many of the actinide elements. It is clear from this graph that fission will produce neutron-rich daughter products, and usually is accompanied by the release of free neutrons, giving us some idea of the limits of the location of the neutron drip line for higher values of Z. Now, in general, any given isotope will show a single decay mechanism, or perhaps I should say a dominant decay mechanism, and each particular decay follows first-order kinetics, which are usefully characterized by a half-life. The values of the half-lives vary wildly from one nuclide to another, although not in an entirely unpredictable way. So for example, if we have a sample of uranium-235, this isotope decays by emission of an alpha particle, and the half-life is 700 million years. When it decays, it forms thorium-231. This isotope of thorium decays by beta emission and has a half-life of just 26 hours. It transmutes into protactinium-231, which has a much longer half-life of 33,000 years. And when it decays by alpha emission, it forms actinium-227. You can see that for each particular isotope there will be a sequence of elements, a sequence of nuclides, a so-called decay series. Now occasionally the energetics are such that we may see a single isotope undergo 2 different decay mechanisms. This is the case for the isotope of actinium-227. This isotope has a half-life of 22 years, and for the most part actinium-227 undergoes beta decay and forms thorium-227. But sometimes, about once in every 100 decays, actinium-227 decays by alpha emission, resulting in a nucleus of francium-223. Although this bifurcation results in two different daughter products, it turns out that francium-223 very quickly decays by beta emission to form radium, and the other element, thorium-227, that decays by alpha decay to give the same radium isotope, and thus the series reconverges. For elements up to about lead, radioactive nuclei are either neutron-rich or neutron-poor, and they generally decay rapidly to a stable isotope. For the heavy radioactive elements, the decay generally moves them along the valley floor, with a gradual loss in mass until they reach a stable isotope of lead or thallium. Despite the many radioactive elements and isotopes beyond lead, there exists just 4 important decay series. This is because of the age of the Earth. So much time has elapsed since the elements from which the Earth is formed were created that all the short-lived isotopes have decayed into something more stable. These 4 decay chains map the only possible pathways down the valley of stability. 3 of the pathways are current and active, and 1 is archaic, meaning earlier on in Earth history this process was happening, but at this stage all of the radioactive nuclei have now transmuted into a stable product. The decay series can tell you about the composition of natural radioactive minerals. For example, in a mineral deposit of uranium or uranite, initially it will contain just the 2 stable isotopes of uranium. That's uranium-235 and uranium-238. Both of these have very long-lived nuclei, meaning that the uranium is only weakly radioactive. However, when we measure the radioactivity of a natural sample of uranite, we find it to be much more radioactive than we might expect. And that is because when uranium decays, we get many more radioactive species being formed, before we ultimately end up with stable lead. In fact, if enough time has elapsed, the proportion of decay products in our mineral sample of uranite will be the same as the proportions of the size of the half-lives of each of the nuclei in the decay chain. Okay, that'll do for now. We've looked at a lot of aspects of radioactivity in this unit, and we'll look at nuclear fission in a little bit more detail in the next video.